Hi and welcome to this transition year higher level maths geometry revision module video. This video has been put together as part of the geometry revision module, which is to help you revise what was covered at junior cert higher level and to help you as you move into the Leaving Cert higher level maths course. This video is going to focus on triangles, and in particular we're going to cover types of triangles, properties of triangles, and the exterior angle of a triangle, right angle triangles, congruent triangles, and similar triangles. So let's first start by looking at the types of triangles. So there are a number of types of triangles, and one category of triangles is putting them together based on their sides. So an equilateral triangle has 3 equal sides. An isosceles triangle has 2 equal sides. A scalene triangle has no equal sides. To help you to remember that, think of equilateral, which is coming from the Latin terms equal, and lateral side, so equal sides. Isosceles actually means 2 legs, so that is the 2 sides of the triangle which are the same. Scalene has no sides that are the same. We could then think of the types of triangles based on their angles. So an acute triangle, all 3 angles are less than 90 degrees. A right angle triangle has one 90-degree angle, and an obtuse triangle has one angle that is greater than 90 degrees. So let's look at what is one of our first theorems that we've ever learned, and that is most useful as we're working with triangles. And that is that the sum of the 3 interior angles of a triangle will always add up to 180 degrees. And you will need to prove this at junior cert higher level, but for now we're going to accept the fact that both those 3 angles, in this case A, B and C, add up to 180 degrees, and we can use this to work out missing angles in a question. Let's talk about some properties of triangles. These are often things that are covered very quickly and students forget, but they can be the most useful things as we're working on certain questions. So the first property that is important is that the sum of the lengths of any 2 sides of a triangle must be greater than the third. So if you choose any 2 sides, add them together, they have to give you a number bigger than the third. This is extremely useful if you are given 3 values for sides and asked, can you make a triangle? Because sometimes you won't be able to, and this is the property. So the 2 sides will always add up, or the sum will always be bigger than the third side. The next piece of information we have about triangles, which can be hugely useful, is that the biggest angle in a triangle is always opposite the longest side. And the opposite is true. The side that is opposite the smallest angle is the shortest side, and the third one would be that the middle angle, so the angle that's not the biggest and not the smallest, will be across from the side that is not the longest and not the shortest. So that helps us to make some judgment calls as we're doing questions and they ask us about the biggest angle or the smallest angle in a triangle. So the next theorem you would have learned is called the exterior angle of a triangle. It's hugely useful, and again this is one that you would have had to prove formally as part of the junior cert higher level course. So it states that the exterior angle in a triangle is equal to the sum of the 2 opposite interior angles. In this example here, it's telling us the size of A plus B is the same as D. And the reason for that is, if we look at our diagram, this whole angle here is a straight angle, so it should add up to 180, including the little piece of red I've just done. And similarly, this little red angle plus A plus B should add up to 180, because all angles in a triangle should add up to 180. That can then be used to prove that A and B will add to give us the same as D. So let's look at an example which uses some of the theorems we've looked at so far. Find the value of x in the diagram. Well, we could use either working with our straight line, working out this angle here, and in turn using 180 degrees in a triangle. Or we can go even simply and say, well, I know that the 2 interior opposite angles, so 47 degrees plus x degrees, should equal the external or exterior angle. So you get x is equal to 102 minus 47. So what we get here, 65 degrees. Now let's look at a second example. If you have not already done so, it would be a good idea for you to revise the angles video, which covers alternate and corresponding angles. We're going to use a little bit of that as we work through this example. So in the diagram below, it shows a parallelogram. One of the sides has been extended. The size of some of the angles are marked. So our focus should be on the fact that we have a triangle, really. And the triangle I'm going to focus on is this triangle here, because I'm looking for all the angles in this triangle. This triangle has then been extended. So the first thing I'm going to note is this. I know that h is the external, so I know h is going to equal to f plus g. We just talked about that. So if I could work out f and I could work out g, then I'll be able to add them together to get h. But first now I need to figure out what is f and what is g. Since we have a parallelogram, I can say that these two sides are parallel, as are these two sides. So working, there's a few different ways you could work, but working with this particular parallel line and this one here, and they're transversal here. So transversal is a line that cuts across two parallel lines. I can say that 45 degrees and f are alternate angles. Therefore, they are the same size. So f is 45 degrees. Similarly, I can work and I can work like this, up, across, and up, and I can say that G and 25 degrees are also alternate. So here I can say G is 25 degrees. I've already said that if I add these two together, I get the value of H, which is 70 degrees. So be careful in questions where they're asking you to calculate rather than measure. Here they've been very clear and said do this without measuring. It is important to note that in many exam questions, and including questions in the book, the diagrams in the questions are not drawn to scale, so measuring will not get you the correct answer. So let's just do a really quick revision on right angle triangles. So I have a right angle triangle here. A right angle triangle is one that contains a right angle. Do be aware that it's important that you never assume that it's a right angle triangle. There is always something to indicate, like our square here, to tell us that that is a right angle. Right angle measures 90 degrees. And a really important word that you need to know is the word hypotenuse. So a hypotenuse is the longest side of a right angle triangle. Now sometimes that can be difficult to spot if there's very little difference between the sides and if the triangle itself has been rotated. So another way to remember where the hypotenuse is, it's across from the right angle. So the side that is across from the right angle is always the hypotenuse. So Pythagoras' theorem, what he discovered was in a right angle triangle, the square of the hypotenuse is equal to the sum of the square of the other two sides. So let's take a look at this. Here's my hypotenuse here, my longest side. Here's my right angle. What he discovered was this length of this side is 5, and if I drew a square, which is 5 by 5, it would have an area of 25. The other two sides have a length of 3 and 4 respectively. This then has an area of 9, the square on the side of 3, and the square on the side of 4 is 16. And what he discovered was that 25, the big square, is equal to the two smaller squares added together. So this can be simplified into our formula and used, but sometimes it's important for students to see this visually to really understand what he was talking about. So this picture here, hopefully you can see drawing your squares on each side. So if we want to simplify this, we can use the formula which is on page 18, and it's c squared is equal to a squared plus b squared, where c is equal to the hypotenuse. It doesn't matter which arm you label A and which arm you label B. The important one is C. So once you get C correct, the other two do not matter. So now let's use Pythagoras' theorem to help us to work with some questions. Use the diagram on the right to calculate a value for x. Give your answer in third form. So that's important. That's working with our square roots. So first thing I'm going to do, I label my triangle CAB. I then write down my formula, which is c squared equals a squared plus b squared, which is x squared is equal to 3 squared plus 3 squared. X squared is equal to 9 plus 9. X squared is equal to 18. X is equal to the square root of 18. So x, when that is simplified down, although square root of 18 is in third form, it's not in the simplest third form. So we can simplify that even more and we get 3 root 2. If they asked us to convert that or to give the answer to so many decimal places, that would easily be done from our calculators. The second example, find the length of the short side in a right angle triangle. So here we're looking for the value of y. Again, give your answer in third form. So again, first thing I do is I label CAB. I write down my formula. C squared is equal to a squared plus b squared. C is 3 squared is equal to y squared plus 1 squared. 9 is equal to y plus 1. Y squared plus 1. So what we want to do is we want to subtract 1 from both sides. So 8 is equal to y squared. So just flipping that to make it easier. Y squared is equal to 8. Y is equal to the square root of 8. So in this case we get y is equal to 2 root 2. So again, it's important you don't leave your answer in the third form you get, but that you simplify it as much as you can. So now let's talk about Pythagoras' theorem and also the converse of Pythagoras' theorem. So Pythagoras' theorem is one that sits between both trigonometry and geometry. So because it sits in both, we can look at it from more of a trigonometric point of view. So working with Pythagoras before working with our sine, cos and tan or our trigonometric ratios. Or we can look at it from a more geometry point of view. So we might be using Pythagoras' theorem and then work with our other theorems we have from geometry, such as all the angles add up to 180, etc. So here we have the theorem of Pythagoras, which basically tells us that the square of the hypotenuse is equal to the sum of the squares of the other two sides. This is specifically when we have a right angle triangle. The converse of this theorem says if the square of one side of a triangle is the sum of the square of the other twos, then the angle opposite the first side is a right angle. So basically, if we don't know that the triangle is a right angle triangle, we can use the Pythagoras' theorem to prove that it is a right angle triangle. And we know then whatever side is the longest must then be the hypotenuse. So this leads us to something called Pythagorean triples. So this is a term that does tend to come up and we've seen it at both junior cert and leaving cert. And basically the term Pythagorean triple means three numbers such that put into the formula they satisfy c squared equals a squared plus b squared. So the example here is 3, 4 and 5. They form a Pythagorean triple because 5 squared is equal to 3 squared plus 4 squared. And remember, the hypotenuse when we're talking about a right angle is always the longest side. So this will always be the square of the longest side, or in this case the biggest number, will equal to the sum of the squares of the other two numbers. So there are infinitely many Pythagorean triples, but here are some examples. Often as students work with trigonometry, they start to notice these Pythagorean triples and they start to notice that when you have 3 and 4 and you're missing the hypotenuse, hypotenuse will always be 5. So they start to see these patterns emerge. So we have 3, 4, 5, 5, 12, 13, 7, 24, 25 and so on. Now let's look at an example which uses the converse of Pythagoras' theorem. So Maisie writes down the following theorem. If a triangle has sides of length 3, 4 and 5, then it is a right angle triangle. State the converse of Maisie's theorem. So basically the converse is working opposite. So if a triangle has sides of length 3, 4 and 5, then it is a right angle triangle. So the opposite is if a triangle, and your wording is not 100%, it doesn't have to be exactly like I would write it, as long as you're saying the same thing. So if a triangle is a right angle triangle, it will have sides of length 3 centimeters, 4 centimeters, and 5 centimeters. So is the converse of Maisie's theorem true or false? Well, it's false, because just because it's a right angle triangle doesn't mean it'll have the lengths 3, 4 and 5. Yes, 3, 4 and 5 mean that it is a right angle triangle, but the converse of this is not necessarily true. And that's an important note about the converse of any theorem. So sometimes the converse is true and sometimes the converse is not true. For example, if you are a student in St. Leo's College, you are a female, and that is true. However, is the converse true? If you are a female student, you are a student in St. Leo's. No, you don't have to be. Just because you're a female student doesn't mean you have to go to St. Leo's College. So just because it works one way doesn't mean it will work the other way. In some cases it does, and Pythagoras' theorem, it does work both ways, but in the case of Maisie's theorem here, it won't. So is it true or false? Justify your answer. Well, it's false. A right angle triangle can have sides of lengths other than 3 centimeters, 4 centimeters, and 5 centimeters. So it's important to remember what we talked about on the previous slide, the fact that there are infinite number of Pythagorean triples. So that means that there are an infinite number of right angle triangles that we could create. So it's not just this one in particular. So now let's talk about congruent triangles. So congruent triangles are triangles that have the same shape and the same size. So the shape of a triangle, that is controlled based on the size of its angles. So that means that the triangles have the same size angles. Its size is then dictated by the length of each of its sides. So what that means for congruent triangles, it means that the corresponding sides are equal and the corresponding angles are equal. So congruent is just a more mathematical term for identical, and we talk about shapes of all kinds being congruent or identical. The symbol for things being congruent are 3 lines, so it looks like it equals with an extra line. So there are 4 ways which we can tell if triangles are congruent. So the first is side, side, side. If we have 2 triangles and the 3 sides are all the same lengths, so as in they could be 3 different sizes on one triangle, but the second triangle mirrors those sizes, that means they are identical. The next one is SAS, which stands for side, angle, side. Now, the way that that's written is really important. It's not any 2 sides and any angle. It is 2 sides and the angle which sits in between. So SAS, the way it's written, side, angle, side, you can see that that angle sits between the 2 sides. In our diagram here, you can see that that angle that we're talking about, that is in green, is clearly shown between the 2 sides marked. The next type of property we have for proving congruency is ASA, which stands for angle, side, angle. And again, the placement of this is very important. It is 2 angles and the side that is in between. The last one we use is RHS, which stands for right angle, the hypotenuse, and one other side. This is specifically for right angle triangles, and it does not matter which of the other 2 sides we know. So if you're ever to ask, are these triangles congruent? We want to be able to justify our answer using one of these. It's important to note here that angle, 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 so three angles being the same, does not necessarily mean they're congruent. They could be, but you need more information than that. We'll talk about those type of triangles in a further slide. So let's look at an example that asks us to prove congruency. So Dara is using a compass and a straight edge to bisect the angle ABC. His construction lines are shown on the diagram below using the dotted lines. His points D, E and F are labelled. Dara says that DF is equal to EF. So let's look at the diagram and see what he's talking about. So he says this line here is the same as this line here. And is he correct? And the answer is yes. So if you have not already revised your constructions, do so. There are links to some very good videos on YouTube which go through how to do the constructions. This one is bisecting an angle or cutting it in half. But when we do this, we open our compass and we put in the arc which cuts the arms of the angle at D and at E. We then place our compass at D and draw an arc to create this point F. So we put our compass point at D and again at E. So we would open this compass the same size, so they would have to be equal. So is he correct? So explain why he is correct. So what I'll do is I'll talk through it here just because I haven't left myself enough space to write it. But from the construction, the same length is used from D to F as E to F because the same opening size is used as we draw this arc here and when we drew this arc here. So that means that they are arcs of the same radius, therefore DF and EF must be the same. It says, now draw in the line segment DF and EF, which we've done. Now prove using congruent triangles that the line BF bisects ABC. So really what we're trying to prove is we're trying to prove that this angle is the same as this angle. Because if they are equal, that in turn proves that the line BF bisects ABC. So they've already given us this huge hint and they've said using congruent triangles. So we're going to work with two different triangles and we want to prove that they're congruent. So the first triangle I'm going to work with is BDF. So it's this one here. So B to D to F. So that triangle there. Okay. And the second triangle we want to prove is congruent is BEF. So this is the one that comes out here. So we want to prove that they're congruent. So this is a really good chance for us to practice how to very strategically display our answer when proving congruency. And we'll use this in other questions as well. So the first thing we do is we label the two triangles that we're going to work with. And what this does is it lets you keep everything quite clear which triangle you're dealing with. So the first thing I'm going to say, well, I know DF is equal to EF. And we know that that's true because of part I. Okay, we've talked about this. That is given in part I. The next two things I know are the same is BF is equal to BF. Now, of course, they have to be the same. They're the same line. So our explanation for that is common. So we need one more thing that's the same. We need one more piece of information that we can use. And what we could say is that BD is equal to BE. Oh, sorry now. It should be our straight line. And the reason is it's on the same arc, which means same radius. So we can see that. Okay, so you can see this arc here, and they must be the same length because it's the same radius. Okay, so we've proved that three sides are the same. So therefore, what we can say is triangle BDF is congruent to triangle BEF because we've used side, side, side. So we've proved side, side, side. Now, just be careful. So then we have to actually answer the question. Therefore, all angles are the same. Therefore, the size of angle DBF is equal to the size of angle EBF, and therefore the line BF bisects ABC. So by proving those two angles are the same, and they have to be the same because we have two identical triangles, we can prove that those two little angles are the same. Just colouring what which ones we're talking about, we're saying this size of the angle here is equal to this angle here. And because we've done that, we can say that it bisects ABC. So this is how we could use congruency within a question, but this layout can be very useful to make sure you don't forget anything and to make sure that your answer is very, very clear. So now let's have a chat about similar triangles. So two shapes are said to be similar if one is an enlargement of the other. So similar, if you think of that word in English, it means something that's kind of the same but definitely not identical. So we have two things that are somewhat the same, so they are similar but they are not identical. So in this case, we say that one is an enlargement of the other. So one is a bigger version of the other. So triangles are similar if the size of their angles are the same. So similar triangles can also be called equiangular triangles. So equiangular means equal angles. We don't use that as much, but this as it can be used to talk about a triangle that has all equal angles, but that's more likely to be called equilateral. But we can talk about two triangles are equiangular if their sizes of their angles are the same. That's how we recognize similar triangles. So similar triangles have the same shape because they have the same angles, but are not the same size. So one is a bigger or smaller version than the other. So let's take a look at some pictures. So similar triangles have the following properties. They have the same shape, but not the same size. Each corresponding pair of angles is equal, and the most important piece here, based on one of our theorems, which we're going to look at in a second, and it's the most useful piece of information we know about similar triangles, the ratio of any pair of corresponding sides is the same. Okay, so that is hugely important, and we're going to work through that. So you can see these three triangles here. The first triangle, let's call this triangle 1. So that is big, it is then shrunk down to this, and then this is also rotated. But they are all similar. They're not identical because they are different sizes, but they are similar. And we can tell they're similar because they told us these are all Y. These are all X. And these are all Z. So we can see that they have three matching angles. So equiangular, equal angles. So the corresponding angles are equal. Be careful with the use of corresponding here. When we talk about corresponding, we mean they match within both of the triangles. It has nothing to do with corresponding angles that we've already looked at, where we're talking about angles between parallel lines. So similar triangles, the theorem we look at is theorem 13. So two triangles are similar if their sides are proportional. So PQ divided by AB. So this side here divided by this side here will be the exact same as, let's change colour, PR divided by AC. Now we're going to talk about that as a scale factor, or you can plug that straight into the formula here. Notice that this theorem, the converse is also true. The converse is also true. So if you can show that two triangles are such that their sides are proportional, then you can say, well, actually, these must be similar triangles. So it works both ways. So now let's look at an example of similar triangles. So in the diagram below, MNP, so the size of MNP, so there's MNP here, is equal to P or Q, which is this angle here. Prove that MNP and Q or P are similar. So just like when we were proving congruency, we set up first our two triangles here. I really do suggest that you do this, because often we see students and they repeat the same thing but backwards, and because they've repeated it but backwards they don't realize they've repeated it. So at least this keeps it straight. So anything got to do with triangle MNP we put on the left, anything got to do with Q or P we put on the right. So the first thing I'm going to write is I know that the size of angle MNP is equal to the size of angle P or Q. And the reason is that has been given to us. We've been told that. Okay, the next thing I know is actually this angle here is equal to this angle here. And the reason I know that is because they are vertically opposite angles. So the size of angle MPN is equal to the size of angle or PQ. And the reason is that they are vertically opposite angles. Now, I've proven that two angles are the same. In order to prove that something is similar, I need to prove that three angles are the same. Once you've proven two angles, that is actually enough. So I can straight away say that the third angle must be the same. So PMN must actually be equal to PQR, and the reason is it's the third angle in the triangle. And the reason I can say this is because all triangles must add up to 180 degrees. So the angles in the triangle must add up to 180 degrees. So if you have two angles of the same and they both add up to 180 degrees, by that logic, the third angle must also be the same. So sorry, let me clean this up a bit. So when we're working with similar, it's important to remember that actually just proving two is enough, because the third will always be the same. Therefore, triangle MNP and Q or P are similar. So you just need to remember how we prove similar, and that is three angles are the same. So now let's look at a question that asks us to use the fact that they are similar to find some to find some missing sides. So two triangles below are similar. Find the value of x. Now, what I'm going to do is a bit of color coding here. So I have this angle here that I've been given. The fact that they're marked tells me that they're the same. Okay, so that's the same as this, because they've been marked, and that's why they have been marked. So the other two triangles, I have to be able to work out which ones correspond. And I know that this one would have to correspond to this one here. And the reason I know that is true is because they are both obtuse angles. And there's only one obtuse angle in the triangle. And the third angle here and here must also be corresponding. So that's the first thing we need to do. We need to figure out, well, where are the corresponding angles? What we can do then when we have the corresponding angles is find the corresponding side. So here we're talking about the side labelled X. Now how I identify that side is it's between what I have as the green angle and the blue angle. So here is the corresponding side in this triangle between the green and the blue. So then let's talk about the 25. So this one here. And it's between the green and the red angle, so its corresponding side is here. Okay. So now we can see which sides we're playing with. They are considered corresponding sides, and we can use our theorem to work out the missing side. So I know the yellow side in one triangle, which is x, divided by the yellow side in the other triangle is equal to the green side in that triangle divided by the green side in the other triangle. Which way you do this is completely up to you. I would always suggest that whichever side you're missing, put that on top. It will be the equivalent to, say, 6 divided by x is equal to 15 divided by 25. But what we're getting then is that unknown underneath the line, which just makes our lives a little bit harder. So what I'm going to do now is I'm going to multiply both sides by 6 to get rid of our 6 here, common denominator. X is equal to 6 times 25 divided by 15, and that gives us x equals 10. and that is our missing side. So a little bit of prep work, but that little bit of prep work means that you're not just randomly dividing numbers by numbers and hoping for the best, that you're really seeing how these triangles link together. This one in particular, because of the way they've rotated the triangle, it is a little bit harder to see which sides correspond to which. Sometimes that's a bit more straightforward, but I would always suggest this color coding or some kind of visual aid to help you work through this. So now let's look at another type of similar triangles, and these are very common, and they're where basically we have one triangle within the other. So first thing they ask us is to find the value of x. So we have two triangles here. We have a small triangle, which is here, and we have a bigger triangle, which is here. Now, those two triangles are similar, and the reason I know they are similar is because one has been constructed with a parallel line within the bigger triangle. So that means because of those parallel lines, this angle here corresponds to this angle here, their corresponding angle in the true sense of the word, where there are two parallel lines, and this angle here is 70 degrees because it corresponds to this angle here. So no matter which of the two triangles we look at, we have the same angles, therefore they are similar. So it's important to recognize that. Now we're going to find the value of x. So basically I know when I add my three values of my angles together in any triangle, it should add up to 180 degrees. So 5x plus 70 should give me 180. Taking away 70 from both sides, I get 5x is equal to 110, and dividing both sides by 5, so 110 divided by 5, and I get x is equal to 22. So just be careful, and that's degrees. You sometimes are asked to work out if what are the sides of the actual angles. Here they just said x. So given that AE is 100, so there's 100 from A to E, okay, and AC, so from A all the way to C, that is 130. And DE, so this side here is 74, so that goes from here. Okay, find the value of BC. So we've already used x, I'm going to use y. So we're here now, we have two similar triangles, and we're going to work with these. So the first thing I would suggest you do in a case like this is to draw them out separately. So there's one little triangle, that is AED. Then I have the bigger triangle, but it looks the same shape, should be the same shape, and that's ACB. I have this angle here, they're corresponding, this angle here is corresponding, and this angle here is corresponding. So quite simply now in this question we have corresponding sides. This corresponds to this, this corresponds to this, and this one corresponds to here. Okay, so these are in the same kind of order. It hasn't been rotated, so it's a little bit easier. We have 100 here, we have 75 here, we have 130 here, and we have y here. So now visually we should be able to see we're working with the yellow and the blue sides. I'm going to say the blue side in one triangle divided by the blue in the other is equal to the yellow in one triangle divided by the yellow in the other. Again, I'm always focusing on my missing side first, just to make my life a little bit easier from an algebra point of view. Multiply both sides by 75 to get rid of my denominator here, and we get y is equal to 75 times 130 divided by 100, and we get y equals 97.5, which is the length of BC. So it's all about the setup, and then the rest of the question will flow.